This is Unit 2E. It deals with different types of radioactivity and nuclear radiation. So starting at the bottom, we have the concept of matter, and three building blocks of matter are the proton, the neutron, and the electron, and together they make the atom. So the protons and the neutrons combine in the nucleus, hence nuclear, and we see them there again. The electrons are far smaller. They're on the outside, and they're in shells on the outside of the atom. This isn't at all to scale. It's about 10,000 times wider than the nucleus, so it's very difficult to fit on the page. Now, a process called ionization involves electrons being knocked off or occasionally added, but here we see them being knocked off. And that means that there are more positive charges. There's 1, 2, 3 there, and only two negative charges. So overall, there is a positive charge in this case, and we call that an ion. So we have protons, neutrons, electrons. The protons and neutrons form the nucleus. The electrons are in shells. If they get added to or subtracted, it becomes an ion. So really crucial idea, this left-hand side. Sounds a bit technical, but once you get your head around it, it shouldn't be too difficult. So we have three types of radioactivity here. Alpha, which is a proton, two protons, two neutrons. The way to remember that is alpha has a P in it, and although it's silent, it is the only one of the three that has a P in it, so for proton to help you remember. Beta particles are fast-moving electrons, and again, the way to remember it is there's an E in that. None of the others has an E in it. Gamma has a double M, which looks vaguely like a wave, and that's what makes gamma unique. It is nuclear radiation because it comes from a nucleus, but it is also electromagnetic radiation. So if we start from the bottom here now again, energy spreading out is radiation, so that's a very general term. So we have nuclear radiation, as we said, that comes from the nucleus, and we have electromagnetic radiation, which consists of an electric field and a magnetic field. So on the one hand, you need to keep them quite separate. When you say radiation, which do you mean? On the other hand, gamma falls in both camps, so that's a bit confusing, but again, hopefully with this diagram we can see what's going on. As we can see, it's like a Venn diagram. So alpha, beta and gamma really just mean A, B and C, so there's not very much meaning in their name, but they are named in order of how penetrating they are. So alpha is the least penetrating, so it's blocked by a few sheets of paper, which makes sense because it's the biggest and the clunkiest. Beta is more penetrating. It will fly through, mostly fly through paper, but it will be blocked by a few millimeters of aluminium. Gamma is the most penetrating, and you need a few centimeters of lead to stop that going any further. Now, they can be dangerous, but they are also useful, so we've got a couple of uses here. The first use here is the smoke detector. So this is a picture of one here. This is in the ceiling, obviously, because hot air and also smoke has low density, so it rises. We have a radioactive source here, an alpha source, usually, sometimes beta, but usually alpha. And under normal circumstances, when there's no smoke, the alphas fly through there and they ionize the air. So we talked about ions over here. So ionization is the process of becoming an ion. So we can see here, as it smashes into an air particle, it's not shown, we get this ion being produced. And there is a positive and a negative plate across here, and so we get a current. So normally we get a very small current, but it's enough to be detected. Now if there's smoke, so these are smoke particles, they will block and disrupt the ionization process, so we get less, or fewer I should say, ions being produced, and therefore the current falls, and then we get some kind of alarm being sounded. So we also have paper thickness gauge, so this utilizes beta, so we get a stream of beta going through the correct width of paper. Now if there's some kind of problem in the mill and it gets too thick, fewer will get through, and so again we've got a detector here that will detect that and adjust the roll. So key idea here is radiation, two types, nuclear coming from the nucleus, electromagnetic. Try not to get them confused, although gamma is in both camps. So now let's look at gamma in a little bit more detail. Gamma is also very, very useful. The first thing we're going to look at here is a gamma tracer. So this is in a medical context. Here we have a gamma source that's combined with a particular chemical, and that chemical or compound is chosen because of its binding properties to the problem that the doctor suspects. So it's injected, and after a few hours it will find its way to the source of the problem. And at the bottom here we can see some real gamma images, and we can see a strong gamma signal coming from particular parts of the body indicating problems there. So it pinpoints various diseases or disease areas for us. And here we can see the gamma signals coming off very strongly, and we've got our camera there picking up the signal. So it's a diagnostic tool, a very helpful one. Gamma can also use to treat cancer, and we can see that here where we have a tumor in the brain that can't be operated on in a conventional way, that it would be too damaging to cut through healthy parts of the brain. We have this gamma source, but by rotating it we minimize the damage to healthy parts. So these parts here will still get some damage. It's not something that's desirable, obviously, but they're only being hit a part of the time, whereas the problem area here, the tumor, is being constantly hit and hopefully destroyed. In a very similar way to X-rays, which we deal with in another video, gamma can be used to image in an industrial context. So rather than taking a machine apart, which can be very expensive, a gamma source is put on one side, and a film can detect cracks as it can here. Now, nuclear in general, not necessarily gamma, is also used for nuclear power, which has its advantages. It's very powerful. There's quite a lot of it around, longer than fossil fuels. It's very reliable. It's not weather dependent. It doesn't produce CO2, so those are the advantages. There are disadvantages. It's limited in the sense that we only have a few hundred years. There is an accident risk, and we also have the problem of storing the waste.